All right, so anyway, we have our test is going to be on next Thursday. That's a week from today. Plenty of time. And there's really only one really new thing in the chapter, and I'm going to get to that in just a minute. But this is something that was new, but it wasn't. And you say, what are you talking about? How can it be new and not new? Okay, so what did Galileo say? Galileo said what? Way back in the 1600s, he says, when you have a projectile, what kind of a path does it take? So, any kind of projectile, like right now, it's not a projectile. Now it is.
Parabola.
All right, so it's a parabolic path, right?
Yeah.
And he said, and I read you from his original writings, up to that point, everybody knew it was a curve, but no one had known that mathematically it comes out to be a parabola. Now, we did a little thing the other day where I said, now see if you, I know you can't remember all this because I didn't see you on Wednesday, right? So let's see if you remember, why did I put a dot here and then go up 7 and then go up 5 and then 3 and then 1? What does that represent to you? Well, how about little g? Wait a minute. Does little g only work this way? Or does little g work that way?
Both ways.
That's right, because it's Earth's gravitational constant. So if you go this way, I'll take away 10 meters per second of your speed every second. You come this way, add 10 meters per second every second. Either way, it's called constant acceleration. One's positive acceleration, one's negative, right? But this is a picture of constant acceleration, the 1, 3, 5, 7, or 7, 5, 3, 1. Now, what was this a picture of? So I know that's little g stuff, isn't it? That's the force of gravity is going to cause constant acceleration in this direction. But what about a projectile? What about this way? What about horizontally? What's it doing? And why did I do, yes, what is it? Now, why? Most people can't tell me why. Why did I put it 2, 2, 2, 2, or 4, 4, 4, 4? Why was it constant speed? I know what the Earth's gravity does to objects vertically. It gives them constant acceleration. But what in the world is giving this saying constant speed horizontally? I bet you know. Yes, inertia. And Galileo said, an object in motion like this way, and again, this doesn't count air resistance, does it? It has a tendency to keep moving in a straight line at a constant speed. Now, we know this thing's not traveling in a straight line because he said it's two motions occurring simultaneously. But I tell you the thing that I thought was ingenious. I don't think I would come up with this. What did he say? They're occurring simultaneously, but they're what? The motions are occurring at the same time. Independent. Huh. What's that? What does that mean? What does that mean? So what if I launch this vehicle at one angle and it goes like that? And then I launch it at a different angle and it goes like that. The fact, this went further because guess what? It had a greater horizontal velocity, didn't it? It was going this way faster than the other one. Wouldn't that affect gravity? Wouldn't it? No, they're independent. I don't care how fast you throw it this way, you're not going to keep the Earth from going, ooh, ooh, ooh. See that? And so a rifle is absolutely parallel to the ground. A bullet comes out, high-powered bullet, same instant, another bullet comes straight down. Why did they hit the ground at the same time? And again, I couldn't get over this when I first heard it. I thought, you're lying. I didn't say it out loud to the teacher. I couldn't understand it. Because I knew that bullet was going really, really far, really far. But what I didn't do, my mind wouldn't allow me to say, but it's going to get there really fast. See that? Hey, so when we're doing that, when you talk about it, and remember, you go home, please don't tell them that you pointed the gun down. You didn't point the gun down. That one's going to win, right? And don't tell them you pointed up because that one's going to win. That one's going to lose, isn't it? But if you fire it parallel, both those bullets hit the ground at the same time. Why? Because he said, it doesn't matter what you're doing horizontally. What's the Earth going to do to both bullets? 1, 3, 5, 7, right? That's right? Hey, okay, hey there. We're doing physics. We're talking about parabolic motion, projectile motion, I should say. So, have you had physics before? Okay, all right. All right, anybody else on this? So really, we already had that in the other chapter about inertia. Remember inertia? And we already had about little g, didn't we? You put them together, and we got projectile motion. All right, you okay on that? I also showed you, this one. Whoops. This is the last thing I showed you on Tuesday, I think. Why is it that when you kick a ball or shoot a bullet or whatever at a 15-degree angle, it lands downrange? It lands downrange in the same place as one that's shot at 75 degrees. Have you ever thought about that?
Yeah.
Yeah, the complementary angles give you the same downrange distance. Now, if you think about it, say, well, I don't understand that. Well, this one you would think would go really far because it has a low angle, right? Because if you shoot too high up, it's going to go ooh, and come back down, right? It's not going to go very far. Well, this one should go really far, but guess what? It doesn't go very high, does it? How long can it be in the air? Not very long. And this guy can be in the air a long time, but he's not going this way very fast, is he? He's going this way. And so the complementary angles land in the same place. Again, this is not counting air resistance. They even have a picture over here. The actual path might be quite a bit shorter depending on what it is. Like a baseball might land quite a bit shorter. A pointed projectile, the kind of not a whole lot of air resistance on it, might be closer, might land closer to the real path. In a vacuum, it would travel that way, like that. Anyway, the Olympic Development Camp, of course, they want to try to make athletes as good as they can. So if you're a shot putter, what if you throw the javelin? I'm not sure they have the javelin anymore. I think they got rid of it. Somebody got hurt. How about the hammer throw? Do they still have that? You know, you take this great big thing. Ever seen that hammer throw? Do they still have that? All right, what about the discus? Do we still have discus in track? Okay, I guess you don't get too hurt. Anyway, they would do all that, and look at this. Even the long jumper, triple jumper, they would do the same thing. They would put all kind of dots in their body, and they would turn them into a physics model. And then they would say, what's the speed of your leg, this, that? What's the angle of takeoff? And what angle are they trying to get maximum distance downrange? What angle gives you the longest, the most downrange? What is it? Somebody said it. 45. Now, I did read an article once, and they said because of air resistance, they sometimes try to shoot for around 47. And 47 is about, gives it to them pretty well. So if you're a shot putter and you're throwing at like 35 degrees, you might be very strong, but we can get that ball to stay in the air longer. If you're that strong, we need you to go around 47 degrees, and then it'll stay in the air long enough, you'll get the Olympic medal.
Did you tell Mason that?
Is he do shot put?
Well, him and Ian resist.
Well, I'm hoping that they learn a little bit here, and I'm not trying to say if somebody could videotape them and try to figure out their angle, Now, of course, if you throw it too high, if you throw it like a 75-degree angle, it's going to go up so high, it's not really going to go far down range, is it? So somewhere, if they can shoot somewhere around 47 degrees, they could maximize theirs. All right, you okay on that? That's kind of good stuff. This right here, did I show this picture? I think I might have.
Ended on the last.
Okay. Here's this Galileo guy again, and man, he's good. He was good. He saw things that other people just didn't see. It was right in front of them, but he saw it and they didn't. That's what a genius is. I'm not a genius because I can understand what Galileo said. I'm not a genius. But if I was back then in the 1600s and I figured this out and nobody else could think that way, all right, then you can call him a genius. Okay, so I want you to think about this. Imagine that a cannon is going to fire a cannonball. And as soon as the cannonball comes out, God has a switch, and it's on the gravity switch for the Earth. Ready? Boom! And he turns the gravity switch off. Now, what is a cannonball going to do if there's no gravity acting on it?
It's just going to keep going.
Yeah, but what kind of motion? Let's be big boy and girl, 11th grade. What's it called? Constant speed. So ready? You should cover this far in 1 second, the same distance in the next second. You should go off in a straight line at a constant speed. What's that called? Starts with I? Wait. What's that called? Wait. Do I have to call him Patty again?
Is it inertia?
Yes.
Okay.
Okay. It's inertia, isn't it? Now, here's what Galileo figured out. This is where you should be 1 second later, 2 seconds later, 3 seconds later. But you know where we find you? 1 second later, we don't find you there. We find you below that point. How much? About 5 meters. Okay, oh, it didn't mean anything to me. 2 seconds later, you should be here. Well, you're not. We find you 20 meters below that point. That's just no number for me. 3 seconds later, you should be here, but we find you 45 meters below that point. And, what's that mean? Did anybody have a little aha phenomenon, a little light bulb come on and say, oh, I know what those numbers are. What is it? What is it?
No way.
It is the free fall. How far will an object in free fall at the end of 1 second? 5 meters. At the end of 2 seconds, remember d equals 1/2 gt squared? At the end of 2 seconds, how far does it go? 20. At the end of 3 seconds. So I want you to think about this. That's so weird. You should be here with no gravity, but gravity made you fall. Wait a minute. Made you fall away from a straight line 5 meters. 2 seconds, gravity made you fall. And by the way, it doesn't go here and then fall. It's falling the whole time, isn't it? It's falling away from a straight line. Now look at me. It's falling away from a straight line, the same as if you dropped it, right? It's in free fall. It's going that way, but it's falling at the same time. Now this is for another chapter. Another chapter, I'm going to ask you about why astronauts are weightless. And you're going to say, well, they're so far away from the Earth, or the gravity's not. That's not true. That's not true. There's plenty of gravity when they're in orbit. Then why are they weightless? You know what they're doing? If you could turn the switch off on gravity, here they are in the space shuttle, okay, or whatever, and turn the gravity switch off. What's it going to go? I'm going to go off in a straight line. So I was going around the Earth. You turn the switch off. I'm going in a straight line. Now, if I go in that straight line, ready? 1 second later, I should be over here. But with the gravity switch on, I don't find you over here. Where are you? I fell. Which way do you fall? Toward the Earth? I fell the whole time. I was falling every millisecond. I was falling away from a straight line. And what would happen if I was in an elevator and you cut the cables? I'd be falling. You know why? Because I'm falling. Now, when you say astronauts are falling around the Earth, they're not getting any closer. Because 1 second later, they should have been here, but they're here. Then another second later, they should be here, and they're here. And that's called an orbit. I'll do that later in another chapter and do a little more detail on that. But this object is falling away from where it would have been. And the same numbers you would have saw on the free fall, I don't know about you, but it's some beauty. Isn't there some beauty to that? I know there's some mathematical beauty to this. And Galileo was able to figure this out. All right, what I'm going to do now is we're going to do, let's go, back on that back table behind Sarah. I want you to pick up a ruler and pick up a packet, okay? And this is a packet I'm going to have you work on. We're going to work on it today, and then you're going to try to finish it for Monday.
Mr. Payne, would you mind if I got one of these sheets?
Oh,
I wasn't here that day.
okay. There you go.
Thank you.
And you may not have seen what I was doing there, but I have the video if you want to rewatch the video for that day. Yeah. If you had that with you and you watched the video for about 15 minutes, you'd see what I did.
Dude, Vincent Weinberg, I said to copy it. Alright, I said to take all.
Yes, repeating the joke that someone did 5 seconds ago.
Well, I am
Funnier.
Yeah, but I told him to do that thing. I know he was gonna steal my joke.
All right, now, so everybody get a ruler and a packet. All right, now, before you do anything, hang on. Before you do anything, there's a reason why I'm doing this. The first part of this packet is something you did on another packet, but that's going to remind you of what you did that time. And then I'm going to show you something brand new. Okay? So let's go ahead and do the old stuff first. So I have a ruler, and you can measure it. Now, what I want to do is it says use the parallelogram rule to construct the resultant. So when you add vectors, the answer is the resultant vector, isn't it? So how do I add this vector to this vector? You should not have forgotten this by now. What are you going to do here? What are you supposed to do to add vectors? Uh-oh, you should not have forgotten this. Parallelogram method says take this vector and reconstruct it over here parallel to the first one. Let's do that. Now it's a vector, so we got points taken off because you just drew lines. It's a vector, right? Now, what do I do with this vector? What am I supposed to do with the second vector? I'm supposed to recreate it over here also, aren't I? Now, I'm still not done, because what's the answer? What is the answer after you make your parallelogram? What's the resultant vector? Is somebody, what did somebody say?
Asymptote.
Asymptote? Wait a minute. Wait, asymptote. I thought, okay, never mind. I won't make a joke about that, but no, that has nothing to do with this. It's a funny word, and I do remember when I was in high school and I had to say it, I thought, am I allowed to say that word? But anyway, so yes, I thought it was funny. It has nothing to do with this. An asymptote is a line that comes incredibly close and never, even at infinity, never touches that line. It's, okay. All right, well, anyway, what we have to do, though, I think you meant diagonal. Okay, so the resultant vector is the diagonal. Oops, I missed it. Dang it. Sorry, that was asymptotic. Now, so now, the reason we're reviewing this, I'm glad we did review it, because some of you forgot the parallelogram method. Let's go ahead and do the next one, and let's do a hard one. This one would be kind of hard. Let's do that one. Okay, so I'm going to recreate that vector, and I know it's 3 long, and I'm going to go up here, recreate that vector, and I'm going to recreate that vector. And again, the answer's not there yet. The answer's not there. I have to draw the diagonal, don't I? All right, anyway, I'm not going to do all these right now because that's just review, but I want to show you something new. Does everybody see that? So what is this vector plus that vector? It equals that one, doesn't it? This is important. What the new thing I'm going to show you is the reverse of this. So what's this vector plus that vector? It's that one. Yes, no? Now in the book, here's a question I also, when I was young, I thought the person was lying to me. He said, can a sailboat travel faster than the wind that's pushing it? And I thought about it, and I said, there's no way. There's no way. How can you go faster than the wind that's pushing it? Can a surfer travel faster than the wave that's pushing it?
Yes. Because of vectors.
Why do you say that? Why do you say the surfer can go faster than the water, and yet you tell me a sailboat cannot go faster than the wind? Yes, no? What's going on there? Some of you very quickly must have done something like surfing and saying, oh, you can go faster. Any of you here have done, anybody here done any sailing? Any of you? Okay. Does the sailboat travel faster than the wind? You're right. Now, can a sailboat travel against the wind? If the wind's going this way, Can the sailboat come toward me? Yes.
Oh, get out of here, sailor.
Can a sailboat travel faster than the wind? Yes. Can a surfer travel faster than the wave that's pushing it? Yes. Now the question is, how in the world is that possible? Can an airplane travel faster than the engine's ability to fly it? If the engine's ability says, when you set the throttle here, then 650 miles an hour is the maximum. Can a plane travel faster than 650 miles an hour when the throttle is at maximum at 650 miles an hour? Yes. Now, you know the next word out of my mouth starts with a V. How is this possible? Vectors. Now, let's try this. And the reason I need to teach this new thing about vectors is that you need to understand that you just told me that this vector plus that vector can equal a vector bigger than either one of them. Isn't that what you told me?
Yes.
You told me this vector here is bigger than either one of those, isn't it?
Yes.
So when you add two vectors together, you can get an answer. The magnitude is bigger than either one of those sides, can't you? So if you look at a surfer, all right, it's true that if this is the wave, if he has his board pointed straight toward the shore, he can only go as fast as the wave that's pushing him. But by angling the surfboard, even a boogie board, by angling it, you have two motions that are occurring. There are two motions occurring at you at the same time. You have a motion that tends to make the surfboard go toward the shore, and you have a motion that makes the surfboard go not toward the shore, but along the wave. Isn't that right? So by angling it, you're going to have a speed going this way and a speed going that way. What do you think this plus that equals? It's going to be bigger than that. That surfer will, this is how fast he's going to go. He's going to go that fast. That's faster than the wave. Now imagine if he keeps doing that. He or she keeps doing that. What if you keep doing that? Now you're going faster. And now what's going to happen, if you go faster this way, this component starts getting bigger and bigger. You're going along the way this way, faster and faster, and now look what happens. That surfer can go incredibly faster, a lot faster than the wave that's pushing him. Now, they have an article, I'm trying to think what this book still has, it might be in the back, but there's a whole page if you want to read about how sailboats work. And sailboats, yeah, if I just put a flat sail up and I'm going to go that way and the wind's going that way, I can only go as fast as the wind. But they angle the sail, don't they? And it's kind of like vectors now. Now, part of the push is pushing me that way, and part of it's pushing me that way. And now I have two vectors. And all of a sudden, my boat starts going faster and faster. I know you don't do this, but every time I have car duty, and today it was not very windy, but I love watching those planes. So those planes, the planes, when it's not very windy, the plane just kind of comes and here's the plane's wings, okay? Coming right at me, just stays like that. But many times if there's a little bit of breeze, you watch the plane and it goes like this. Yeah, it's facing this way, but the plane's traveling this way. And of course they have computers now, and they can put those vectors together and say, I want to land on that runway, but there's a wind. Well, then you better not point at the runway. You better point over here because then you'll get to the runway. And same thing with pilots. Pilots know, and if you've ever been on a plane, sometimes they say, well, we had a good headwind or a good tailwind. We had a good tailwind. All of a sudden you get to your city an hour earlier than anybody thought you'd get there. That's because you had your own vector and the wind came behind you. Your plane went faster than it's capable of going. What if you have a headwind? You're going to get there a little later, aren't you? So they try to figure this out, all this weather stuff, and that's how they predict when they're going to show up. Now, if something changes, they'll be wrong, but like that. Now, so what I'm going to do is show you something that is the opposite of adding vectors. Okay, here we go. Did you know that when you throw a ball, it has a certain speed that comes out of my hand? So let's predict It just left my hand, and I'm going to draw a vector representing the velocity of that ball in that direction. You get that? True or false? That ball traveling at that angle right there, part of the ball it's a velocity, part of the ball is moving up, isn't it? Isn't the ball moving up?
Yes.
It has a certain speed going up. What else does it have?
Trying to speak on.
It has a speed going sideways. And guess what? If this plus that equals this, then what does this equal? This equals this plus that. And you might ask yourself, why? Why do I need to resolve vectors? That's what they call it. We're going to resolve vectors into its horizontal and vertical components. And this is pretty neat stuff. So let's try. Now, take your, let's go down here. It's the opposite of adding vectors. We're going to resolve vectors. Now, how do I do this? The first thing I'm going to do is I'm going to take this parallel line here, and I'm going to go over here. And I'm going to draw a little dot right there. Okay? And then I'm going to take this line, and I'll go over here, and I'll draw that here. Okay, now what I've done here, now I'm going to save myself a little bit of time. I don't want to draw I can draw the whole parallelogram, I could, but I'm just going to go ahead and draw the two vectors that cause this to happen. So, when you throw an object in the air, for example, it has one part of its motion is what they call vertically. That object is going vertically at a certain speed, but it's also going horizontally at a certain speed. Got that? Okay, now, so this one, if I were adding these two vectors, I'd get this, wouldn't I? Wouldn't that be my result? So what if I resolve my vector into its vertical and horizontal components? Let's try another one, ready? Now, this time you throw the ball not at this angle, you throw it at this angle. Let's see what difference that makes. What difference does it make if I throw the ball at a higher angle? Anybody see what I'm doing here? Now, I want you to look at the difference here, okay? Now, this vector here happens to be the same size as this vector. But if you throw a ball at this angle, and you throw a ball at this angle, what's going on? What is the speed of the ball horizontally? Which one has a greater horizontal speed? I'm looking at this guy, aren't I?
Sir.
This ball has this tendency to go horizontally. This ball only has this tendency right here. Wait, I gotta find out if you're with me or not. Is everybody with me? Okay, so if you think about it, if this ball is in the air for 3 seconds, it'll go this far every second. That's its horizontal speed. How far will this go in a second? Only that far. Let me travel for 3 seconds. Let me travel for 3 seconds. Who's going to go further downrange?
Left one.
The left one.
Sir.
Okay, let's throw it at a, let's try another one. Well, let's try a hard one. This one has no lines drawn for you. Let's see if you can do the last one. I want you to resolve this vector into its horizontal and vertical components. This has no lines drawn for you, so let's see how you do on that. What do you think? Did it come out to be something like that?
Sir.
Okay, let me give you another example. when you pull a wagon, at this angle, everybody look right here. When you pull a wagon and the handle's really high, that doesn't work very well, does it? You know why? Because when you pull at this angle here, how much of your force is actually going to be used to make the wagon go that way?
Not a lot.
It's like you're using most of your force to lift the wagon. What if I am pushing a lawnmower? I've seen people do this all the time, okay? You push a lawnmower. What if you have the handle up really high, like a high angle? That's not good. Anybody's lawnmower said, that doesn't work very well. Why not? You know why? Because how much of your force is being used to actually make the lawnmower cut the grass this way?
Very little.
And what are you really doing? You're actually end up you're pushing the lawnmower down into the ground. And so you went down here, and now more of your force is being used to make the lawnmower go this way, and less of it's being used to push it down on the ground. You ever thought I bet you never I never thought about that when I was your age. Never thought about that. So when I say you have to resolve vectors, that's why we do that, all right? Okay, let's go ahead, and I know you'll be able to finish that page pretty easily. Now here, this is a great lesson. This is a great lesson. Some of you are going to say, oh, I get it. I didn't understand that before. Now, right here, let's say the person is going to throw a ball, and what do I know is, sorry. Oh, yeah. What do I know is, how fast do you think that ball is going when it leaves his hand? And you might be saying, oh, it must be going 30 meters per second. No, he didn't throw it straight up. Oh, it must be going 5 meters per second. No, he didn't throw it this way.
No, sir.
So how do I find out how fast the ball is actually traveling? If it's going 5 meters per second this way and 30 meters per second this way, let's try it. Uh-oh. Okay. Usually there's meat. And, well, okay, I know what you can do. It'll still work, I guess.
Is this supposed to be? Oh, I see what.
I think it's off by a little bit. Okay, now ready? What speed is the ball actually traveling in its path? If I had a speedometer on that ball, what would it be reading right when it came out of my hand? It wouldn't read 5. It wouldn't read 30. How do we do this? A little math stuff. What do you think? Math stuff. You know why people like to break vectors? They like to resolve them into the vertical and horizontal components so they can do math. All right, here we go. Let's do a little math. See this triangle? It's a right triangle, isn't it? Wait a minute. That's why they do it, to make right triangles. And this is 5, and this is 30. So let's find out what this is going to be. Everybody know Pythagorean theorem, right? Let's do it. A squared plus B squared, that's equals C squared. All right, somebody do it. So it'd be 25 plus 900 equals 925, and I need the square root of that, don't I? Do you have that, Eli?
I don't know.
Square root of 925? Tony?
It's 30.41.
30.41?
Yeah.
So it's a little bit more. Anyway, so the ball at that point is traveling at about 30.41 meters per second. Part of its motion, though, is it's actually traveling upwards at 30 meters per second and sideways at 5 meters per second, isn't it? Let's do another one. Now, here's my question for you, and this is a great question, but why in the world would this component be smaller? What is the size of this vector? Now, this is like crucial right now. This will tell me if you can do anything, connect things in physics. What would be this vector right here? What's the magnitude of this vector? And just raise your hand, and I'll say yes or no, and we'll go to the next person. But who thinks they know what size this vector is going to be? I'm ready. That was half. Yes. You're 2 out of 2 so far. You want to try it? What is it? How'd you know that? You mean what's going to happen to a ball when it goes away from the earth? It will lose 10 meters per second every second? Yes, 3 for 3. 3 for 3. So now, let's go this now. Draw our little triangles here. Whoops, a little too far there. And so now I'm adding vectors, right? I'm adding vectors. Now this is 5, and this is 20. So a squared plus b squared has to equal c squared. So the square root of 425, who's got that? Say it again. Let me say what? 20.62. Okay? Okay, now watch what happens. Something's going to happen now. Now wait, by the way, look at me. When it comes out of my hand, that guy's traveling at about 30.4 meters per second. But 1 second later, it's not. 1 second later, along the path, it's only traveling 20.62 meters per second. Watch what happens next. What goes right there? Everybody in this room should be able to tell me. What goes right there? 10 meters per second. Isn't that right? Now, let's make a little parallelogram method thing again. All right, my triangle would be, oh, by the way, wait a minute. This component went 30, 20, 10. What happened to the horizontal component? 5, 5, 5. Oh, that's not right. Why is that still 5? Somebody knows. Inertia. See? An object in motion.
Only answered.
Okay, now, what's this going to be here? Let's do our little triangle here. Ready? 5 squared plus 5 squared, right? That's 25 plus 25. The square root of 50 is what? 7, what is it? Who's that calculator? Square root of 50. 5 squared. Oh, I'm sorry. Did I say 5? My fault. Maybe mistake. 5 squared plus 10 squared. So 125. What's the square root of 125? 11 point what? I can't hear the last number.
11.18.
Okay, 11.2, right? So anyway, this component is 10. This component is 10. This is 11.28. And what's happening to my ball? If I was on that ball with a speedometer needle, it'd say 30.4, 20.6, 11.28. I'm slowing down, aren't I? Now watch what happens. This is neat. Look at this. What happens at the top? What's the speed vertically? 0. What? And what is it horizontally? And so what is 0 plus 5 meters per second? What? What? Wait a minute. Why does that ball keep moving? Inertia. And guess what? At the top, whether you shoot a free throw, kick a soccer ball, at the top of its arc is the slowest the ball will ever travel in the whole path. It's the slowest. It starts out really fast. It slows down. It's the slowest it'll ever be, and it keeps moving because it has a horizontal component. Now, look at the next one. Let's see if you can do the next one. Ready? Draw the vectors. Now you have to think. Draw the vectors. Now, let's see. I'm going to resolve this vector into its horizontal and vertical component.
This one seems very.
All right, what do you think? What do you think right here? What do you think the size of that vector is going to be? What is the tendency of this object to move horizontally? What's its 5 meters per second? And what's the tendency for it to come speed in a vertical direction? It was 0, and now you add 10 meters per second every second. And now you make this triangle again and say, wait a minute, I think I might have made that before. What is it? 11.25? Okay. And by the way, the speed of the ball here is the same as the speed of the ball here, isn't it? And if you keep doing that, if you keep making your vectors, you'll find out, that what do you think this is? What's this component right here? How big is that? Some of you are getting so tired of answering because you understand this completely. But what's this component going to be? 5 meters per second. And what's this component going to be?
20.
It was 0, and then it was 10 meters per second. Now it's going to be 20 meters per second. And then what's this going to be? I think we did that one before, didn't we? And so the speed right here is the same as the speed right there, isn't it? And then if you do it again, what are you going to get? Same thing as that. And so when it gets to be here, it's going to be going at the same speed as it left the person's hand at about 30.41 meters per second. And what's this component going to be? I'm going to draw this fast. What's the tendency of the ball to go that way? What's its velocity in a horizontal direction? 5 meters per second. And what is it in a, 30 meters per second. I don't know if you see the beauty here. I don't know if you understand that. The way this is all working out, it's like, wow, if you saw the world like this, it's like you would understand a lot of different things, wouldn't you? I think it's one thing I do like about physics is that it really is out there. It's the world you live in. It's physics everywhere. All right, we have time. I'm going to help you this last page because the last page is where people make their biggest mistakes. So I'd like you to get it perfect on this page, on this thing here. All right. So what we're going to do, it says here, above left, use a scale of 1 centimeter equals 5 meters and draw the positions of the ball drop in 1 second intervals. Okay. How far will a ball in free fall if you allow it to fall for 1 second? And you said, wait a minute, I know that. 1/2 GT squared. And you put 1 second in here. 1 squared times 1/2 G is 5. What is it? 5 meters. Now my scale is 1 centimeter is 5 meters, so, oh, I see, there you are. Nah. How far will I fall if you allow me to go free fall for 2 seconds? Somebody said it. 20 meters. Now, 20 meters, it takes 1 centimeter to be 5, so how far am I going to go? 4. And some of you are very alert, and you notice that the distance it fell during the first second, it'll fall 3 of those, or a total of 4, right? What are you going to put? Where are you going to put the next dot? At the end of 3 seconds, how far would you have fallen, your total distance?
About 9.
Times what? What's 1/2 G? What's 1/2 G? 5. What's 5 times 9? 45. The scale says each centimeter is 5. How many? 9? Okay. Okay. And the last one? If you're allowed to fall for 4 seconds. 4 squared is 16. 16 times 5? 80. How do I represent 80 on this scale? How many centimeters do I need to go to get 80? Okay. Now we're not done yet because what they want to do is, and this is great. I love this paper. What if I don't drop it, but I throw it? I throw it straight. And 1 second later, it's gonna be there horizontally, there horizontally, there horizontally. But guess what? There's gravity. If there was no gravity, the ball would do that. If I was out away from any gravitational field, it would do that. But gravity is gonna do this. So here we go again. I gotta be here horizontally, I gotta be here vertically. That means I gotta be here. Everybody got that? What's the next one? I gotta be here horizontally, and what? I have to be here vertically. Is everybody with me? You see what I'm doing? If there was no gravity, I'd be here at the end of 3 seconds, but you won't find me there. You'll find me, I fell the whole time. And I have to be here. See if I can keep this thing parallel. And the last one. Now, it asks you to connect it with a smooth line. Smooth line. Let's do that. All right, what shape do you get? It's half a parabola, isn't it?
Yeah.
And last thing, and then this way, I want you to get this done by Monday. Now, the hardest thing here is the scale. So watch this now. I'm going to do, remember how we did it before? Put the dots in the same place here. But now, this is the hard part. If I throw it at an angle, I should be here with no gravity. But with gravity, I have to fall 5 meters. And what's the scale? Huh? Isn't the scale 1 centimeter? So I have to take my ruler and go like this. All right, what about this guy? He's gonna fall 20 meters, right? How many is that on my scale? Anyway, so if you do that carefully, I think it'll work out for you, okay? All right, go ahead and if you don't mind, put the rulers back on that last table. And I want you could easily have this done by Monday. Be careful about this problem down here. Before you turn it in on Monday, I'll even ask you if you had any problems, all right? Because I want you to do well on this assignment, on all our Millie.